Hi learners, in this session let's try to design Turing machine for some of the languages. Basically, Turing machine as is a representative model of current computational devices can able to support two operations. Basically, any computer will have arithmetic logic unit ALU, right? So arithmetic means any particular system needs to perform arithmetic operations like addition, subtraction, the basic operations, and other additional operations being your multiplication, division, modulo, power, and it goes on depending on the flexibility of the programming language. Now coming to logical operations, if you see, logical means you are going to check the relation between two things. So what are the relations you can check? There are only 6 relations: equality, inequality, greater than, less than or equal to, greater than or equal to. So these relational operations can be combined and put together using your logical operations also. So basically, since every computer will have an arithmetic logic unit, since Turing machine is going to serve as a representative model of or a base model of your computing devices, should be able to support computation of these arithmetic expressions or arithmetic operations or expressions, and should support the relational expressions too or the logical expressions too. So in this session we are going to see some of the pattern matching algorithms. Pattern matching, let's say if we are writing a power n, b power m, let us assume. So we can take it as an equality operator. It may look like, it doesn't exactly mean, it depends on what a and what b means to you. But in general it is an equality checking. Suppose if I want to check whether a plus 1 or a plus b, okay, so c power n, it is whether a is greater than c. So this session will try to see how to design Turing machine for some of such pattern matchings. So a short overview, Turing machine is nothing but a finite automation along with the two-way accessible memory. That is, you can either move towards the left or towards the right. So that's what logically a Turing machine means. So the formal definition of Turing machine goes like this. It's a 7-tuple where 5 corresponds to your finite automata and the other 2 corresponds to the tape, which is accessible in a bidirectional way. So it has finite set of states q, the non-empty set sigma, which represents your input alphabet. Then you have non-empty set of stack symbols or tape symbols. Here, don't mind this, it is actually non-empty set of tape symbols. Then you will have a special state designated as start state and a set of final state, which can say whether you have your particular word has been accepted by that language or not, which is called as a final state. And you will have a transition function where there will be a mapping from current state and a tape symbol to a destination state, a tape symbol, and the direction of movement. Finally, how are you going to represent the tape? Okay, that is the representation using the blank cells, which is B. So this is what a formal definition of Turing machine is. Let's look at the first example. Design a Turing machine to accept strings of the language. The language given is a power n, b power n, c power m, and d power m, where n and m greater than 0. So this is the condition given. So all the strings should have a, b, c, d. So the language goes like this. The minimal length strings, since both n and m are greater than 0, at least one occurrence will be there. So it will be a, b, c, d. A, B, B, C, D, then A, B, C, C, D, D, and it goes on. So this is the language that should be accepted by the Turing machine. So now let's formally look at logically how the Turing machine has to be designed. Let's take one sample word. A, B, B, C, 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 D, D, D. And we know always the input pointer will point to the first symbol. Now what's our intention? The language pattern goes like this. A power n, B power n, C power m, D power m. Where these two to be equated and these two to be equated. So when we are equating A's with B's, we don't need to bother about C and D, and when we are equating C and D, we don't need to bother about A and B. So first, let us see how A's and B's needs to be done. As usual, A's can be replaced by X, meaning that one A is what we have seen on the input. Move towards the right, B replace it with Y. So what X and Y mean? We have seen an A on the input and we have seen an equivalent B on the input. Take a left turn, move towards the left. How long should you move? Until you see a X. Because we don't know how many A's are there on the backward. So the only permissible operation is you can move towards left or move towards right. So what do we do now? Then when an X is seen, take a right turn. Try to replace this A by X. Move towards the right. Replace B by Y. And then move towards the left. Now that after X, we might be expecting an A. A won't be there and instead Y's will be there. So when Y's are there, you have to just skip all Y's till a C is seen on your input. So what does it mean when a C is seen on the input? A power n is equal to B power n. The number of A's is equal to the number of B's. Yes, the process continues. C we can replace either by X or by some other symbol. Let me replace by X itself. Then move towards the right and this D let us replace by Y. Move towards the left until you see an X. Take the next right turn. The next C replace by X. Move towards right. Then replace by Y. Okay. Actually this should be third. Yeah. Then after X, we'll have the third C replaced by X. Move towards right, D replaced by Y. Move towards left. After X, we don't have Y's, rather it is, we don't have D's, rather it is Y. So what should we do? We have to check whether we have all D's converted to Y's. So move till the last and when there is a blank symbol, take a left turn, stop at this point saying that the word has been accepted. If you happen to stuck in any position, let's say when you can't see an equivalent Y. Okay, so after replacing A by X, you'll be moving towards right, looking at a B. When you can't see a B, it means number of A's are more. Similarly, you can write an error location if you want at each and every point wherever you got stuck. So this is how logically the tape is getting executed to check whether the word belongs to the language A power n, B power n, C power m, D power n. We'll try to draw a Turing machine for this. Now, as usual, we'll have a start state Q0. So, what's expected first is A, replace it by X, move towards right. Okay, then you have to skip all A's on the input, then move towards right. What is expected? We have converted an A to X. Similarly, B has to be converted to Y. When we do like so, start moving towards left. Right? So, while moving towards left, what will be seen on your input now? It's all A's that will be there on your input. Keep moving towards left. How long should you move? Until you see an X. When an X is seen, the same procedure has to be repeated and hence I am taking it back to the same state. So, when an X is seen, just move towards right. So, again, if an A is there, replace it with R. Then you move on till you reach this particular point. Okay. So, now this time, when you move, it's not only A's that will be there on your input. You will have Y's also on your input because first B already it would have been converted to Y. Then after converting your B to Y while moving towards the left, you can see here when you change this B to Y, when you move towards the left, you can see and previously converted Y and hence there will be Y's also in your input stream. Right? So till this point when you complete, what does it mean? A power n is equal to B power n. Number of A's is equal to number of B's. Once you reach here, after X, if you don't have an A, what does it mean? unless if you see a Y, what does it mean? All A's are over. So when you see a Y on your input stream, then move towards right. Enter into a new state called Q3. Okay, where you have to skip all Y's and keep moving towards right. So A's are over and equivalent B's are over. So what is expected is to have a C on your input stream. C again, I am going to change to X, move towards right. Then the same process. You don't have any difference. Then skip all C's, keep moving towards right. When you see a D on your input, change it to Y, move towards left. So while moving towards left, you will have C's on your input, keep moving towards left until you see a X. Okay. Now the second C will be converting to X. When you move, it's not only C, it's the previously converted Y is also on your input stream. Then similarly, when you're moving towards left, you will also have previously converted Y's on your input stream. Yes. After this checking, which is for C power M is equal to D power M, is also over, then automatically after X, okay, you will see an Y. So when there is an Y, keep moving towards right. It is Q6. Then in this state, skip all Y's and then you are expecting a blank symbol. When blank is there, keep to move to L, one left, okay, so that you can end up in the last character. Enter into a final state, meaning that the word has been accepted. So which are all the states that corresponds to error entry? When you have an A converted to X, but you can't find an equivalent B. So from Q1, you don't have B, okay, rather you will have C. So what does it mean? And A is already there, which I have converted. So automatically from here, this is 1. I'll write it as 1. So 1 is a dead state. So 1 represents the fact that B is greater than A. Okay. When A is greater than B, what will happen? Sorry. 1 represents the fact that A is greater than B. Okay. A is greater than B. So A already we have converted, but B is not there instead. Now Y is there. So A is greater than B. Then when number of B's are greater than A. So here after X you will see a Y. Right. Okay. After X. Okay. So what will happen? You won't see an Y. Instead you will see a B. Okay. So when you see a B, it means number of B's are greater than A. Similar case when here in Q3. Okay. So you are converting C to X. In Q4 you are expecting a D, but when you don't have a D, it means this is a third error, which is C greater than D. And the final last thing is when C is lesser than D, which is D is greater than C. So what will happen after reaching Q6? From Q3, instead of having a Y, you will have a D, okay, so which is D is greater than C. So when all these things are error entries, if you want to make a perfect diagram from all these points, you have to take the transition to the dead state. So that's how we have to design it. Coming to the next example, design a Turing machine to accept strings of the language. L is equal to A power M, B power M, C power M, D power N. So there exists a concentric circle which we could design using pushdown automata, but the Turing machine is also possible. It's a superset of pushdown automata. Now since n comma n greater than 0, so the minimal length string will be A, B, C, D, and then A, B, B, C, C, D, and then A, B, C, D, D, and it goes on. Now let's see. Let us take a sample word a power 2, b power 3, c power 3, d power 2. Okay, where this to be equated and this to be equated. This is how a sample tape will look like. The input pointer will point to A. I'll just try to convert this to X. Move towards the right until I see a blank. When I see a blank, I can take a left turn and then convert this D to blank. Why am I converting this to blank? Because the first time I am going to use this blank as my representative endpoint. The same I need to retain because for an iterative operation. That's all. Move towards the left till I see an X. When X is there, change A to X and then move towards the right. Skip everything till you see a blank symbol. So before this blank, you are in need of a D. When D is there, change it to blank, move towards left. And after X, if you see an A, that is one case. A is to be equated to D's. If you see a B, that is the second option. B, you change to Y, then move towards right. Now, you again have to reach till blank, but before this blank, okay, the preceding symbol should be C now. When C is there, replace it with blank, okay, move towards the left. After Y, then change the second B to Y, move towards the right. The next blank, C before blank will be transferred to blank, left, and then the final B to Y, move towards left. And then before blank, now you have a single C which will be changed to blank. Now that when you move towards left, after Y, what will be there? It won't be a B, rather it will be a blank symbol, which means the word has been accepted by the grammar. Now let's design a Turing machine for this. You will have Q naught. Okay, so first I'll be looking at an X, replace it with X. Looking at an A, replace it with X, move towards right. Then what are the symbols you need to skip on the way? You will have A's. Then you will have B's. Then you will have C's. And then you will have D's. Everything you need to skip until you see a blank symbol. Then when you see a blank symbol, take a left turn. Okay, so if it is a left turn, then what's expected? To see a blank symbol, what is expected is to have a D, right? Which you can change to blank and then move towards left. While moving towards left, what are the symbols that you will see? Remaining D. Then you will have C is on the path, B is on the path, A is on the path. Everything you need to skip until you see an X. Okay, then again the same procedure continues. A will be replaced with X, move till blank, D replaced with blank, and then this is for equating A power n, D power n. Okay, A's and D's needs to be equated. Now that once this is over, okay, after X, you will see a B rather than an A. So when you see a B on your input, replace it with R, okay, and move towards right. What are the skipping elements now? Remaining B's you need to skip, and then you will have C's you need to skip. Okay, now you will have a blank symbol because D's we don't have since already it was converted. So you will have a blank symbol, then move towards left. When you see a C, okay, because before your blank symbol what is expected now is to have a C. Replace it with blank, move towards left. You can see here, so once these two are converted to blank, before this we are expecting C which we need to convert to blank. That's what we are doing here. You can enter into Q6 again where you can skip all C's on the path, all B's on the path, and until you see a X. Correct. Okay. when you see an X, you have to take a right turn. Then again the same process needs to continue. So I'll just draw like this, where X you have to take a right turn and then move to the same point where it will be expecting another B, and the same process continues. Once both the things are over, when B's are also equated to C's after X, okay, so all B's will be transferred to X. After X, what will be seen is a blank symbol. So at this stage, if you see a blank symbol, then enter into a final state. Okay, similarly here, where and all the error comes. If A's are not equated to D's, where will the error come? Whenever you are expecting that symbol. From Q0 you are expecting A. If it is not there, the first error will come. When from Q2 you are expecting a D. When it is not there, the next error will come. From Q0 again you are expecting B. So third error. Then from Q5 you are expecting C. Then 3 refers to the fact that no B's are there, and 4 refers to the fact that C's are greater than B, in which case you have to enter into a dead state, else you can enter into a final state. Hope this is clear. Wait for more videos.